Hello and welcome. Today I'm going to show you how to run the model for the aerosol and ice nucleation modeling project. And the model is available on my GitHub repository. It's here. So you'll need to download this repository so that it's on your local machine. And the easiest way to run the model is through the Spider interface, which you should have installed and set up. If not, there's a video showing you how you do that. So the first thing to do is to go into the aerosol and ice nucleation modeling folder and then go into Python and open up this py file, runs define. You see, this py file defines a few different variables, and the important one for now is this output dir, which is set to /temp. That just means that the files are going to be output to that location on the Mac. And that should be okay. That should be, because by default temp is writable on the system. But if you want to keep a hold of the runs, you might want to set this to something else, or when the runs are finished, you can take a copy of them and put them on a separate hard drive or space on your hard drive. So next thing to open is the do model runs py file, and then we can run the model by just clicking play here. Incidentally, in the aerosol and ice nucleation modeling project, there are two separate models. One of the models is a standard cloud parcel model that includes aerosol, and it's called the bin microphysics model, BMM. And the other model is called the BDM, or the bin diffusion model. It takes a lot longer to run. So first of all, we run the simple model, the BMM. So we just click play here, and you can see that runs very quickly. It's done one simulation. Next, open up the example plot BMM and run that file by clicking play. And you can see we've got 4 plots here. We've got the mixing ratios, which are plotted for cloud. So cloud goes up and then it goes down. Ice goes up when the cloud starts to go down. That's because the cloud starts to freeze. And also the humidity increases till it gets to about 1 or just above. And when we start to get ice formation, it goes down. This is pressure and temperature. And here we have the cloud droplet number concentration, which goes up. And then when we start to get the ice, it drops down. We have the ice here, which goes up to a maximum. So that's 6,000 per litre, whereas drops we have 4,000 per cubic centimetre, so plenty more drops than ice crystals. And this final plot here are the drop masses. So what we can see is some of the drops grow to large mass and then evaporate. Some of them don't grow at all, so the smaller ones tend not to grow very much. So that's the simple bin microphysics model, and you can save this figure by clicking on here and saving as a PNG or whichever format you prefer. So I'll just close that now. Now the more complicated model is the BDM, and so that's run from this do model runs BDM script here. And as I said, this takes a little bit longer to run. So we're going to click play here. And actually this takes maybe an hour or two to run a single simulation. So you're not going to want to do very many of these simulations. And actually I'm not going to let this finish. I'm going to break out by clicking my mouse in the console window and pressing Ctrl and C. Just interrupt that, because we can still plot some of the output now to see what it looks like. So let's look at example plot BDM. That's here, and click the play button. So that's going to generate another figure. Okay. So this hasn't finished yet, but it basically shows a similar thing to the first plot. And then we've got an additional plot here, which are the profile of each aerosol particle in terms of the radius versus time, and also the water mole fraction. So what it shows here is that the bigger particle does not allow water to diffuse into it very quickly. So that's how you run single simulations. Okay, if you found that useful, don't forget to hit a like and subscribe to the channel. Thank you.